Welcome back. This is our second segment on parts of a hydraulic calculation. Now, this can be a pretty dry subject, but I promise I'll do my absolute best to keep it engaging. In this segment, we're going to identify the direction and organization we need to consider as we get ready to run a hydraulic calculation. Accuracy is arguably the most important part of conducting a hydraulic calc. If we're not focused on getting it right, I guess there's not too much reason to be calculating a system in the first place. As such, there's a lot of prerequisite data we need to identify and then subsequently organize to get this done and to get it done right. Whether you're a sprinkler system design professional and you're hydraulically proving the efficacy of your work, or you're representing a property insurer and the underwriter wants to see a system calculated, or even if you're reviewing plans and calculations done by someone else, we all kind of need the same packets of information. I spent 10 years in loss control and we were required to sketch and calculate every single system. Out of necessity, I got pretty accustomed to organizing all of this data. So buckle up, let's roll. Foundation. Everything needs a strong foundation, right? The greatest fire protection systems we could design aren't going to matter much if the building foundation isn't what it should be. For all of us in this fire protection world, we rely on our training and experience and education to form our professional foundation. MeyerFire University is a great foundational element for each of us. In this case, the foundation of our automatic sprinkler system is the water supply. Whether our water supply is from the public water system in the form of a pressurized water main, or it involves a fire pump pulling from a static source like a pond or a tank, the very first thing we need to do is identify and quantify our water supply. If we're using the public water supply, NFPA 291 is the recommended practice for water flow testing and marking of fire hydrants. Additionally, MeyerFire University has a great course on hydrant testing. If you haven't already checked it out, I highly recommend doing so. So generally, my first data point to collect on a project would be the water supply characteristics. I need to understand a few things before I even begin designing my system. I need to know what the water supply is, and I need to know where the water supply is. In knowing what the water supply is, we need to know, at a minimum, the system's static pressure. That's the pressure in the system with no water flowing. We need to know the available volume of water in terms of gallons per minute, or for metric people, liters per minute. And we need to know the residual pressure. That's the amount of pressure left on the system when water is flowing. Once I have these three data points, we can generate a water supply curve that will serve as our design system's foundation. The MeyerFire Toolkit product is an invaluable resource to crunch all of this data for you. Once we know what the water supply is, we need to understand where the water supply is. NFPA 13 requires our calculations go from the hydraulic remote area we discussed in the last segment, all the way back to the point where the water supply characteristics are known. In the case of a system being supplied by the public water supply, that point is the test hydrant. And because we need to calculate all the way back to the test hydrant, it's critically important that we have a picture of what that network of underground fire line piping looks like. We need to know the size of underground pipe, what it's made of, the locations of any valves, T's, 45-degree elbows, etc. So having a good civil drawing of the underground is pretty crucial. This is so very important that I generally don't even begin any design work until I have it all together. As an example, I currently have a project outside of Austin, Texas, where a new residential gated community is being built. These are going to be a couple hundred very high-end custom homes in a very exclusive community. We have to protect the community's gatehouse/community center. The water system hasn't even been built yet, so there are no fire hydrants for us to test and obtain the fire flow data. The utility contractor designing and installing the underground infrastructure and water treatment plant have said that we can expect a static pressure of between 35 and 87 psi. Clearly, that's not an adequate picture of the water supply. Designing a system with that level of information would be like building a condo building on the shoreline above sifting sands. It's not an adequate foundation. So we've explained to our client that if we attempt to design a system without having all of what we need, everything we design from pipe diameters down to the sprinklers we use, think K-factor, coverage listing, spacing, etc., is just a wild guess at best. When it comes to fire protection, guessing should not be part of our toolbox. This is that important. Occupancy hazard class. If you've ever done anything with fire alarm systems, you're at least somewhat familiar with the occupancy as it relates to the building code. In automatic sprinkler design, what's most important to me is the occupancy hazard class from NFPA 13. We find this in 2025 NFPA 13, Chapter 19. In prior editions, this was located in Chapter 5. This is where we determine the design criteria and design density for the system. This tells us how much water we need to discharge to control or suppress a fire occurring in the system area. It doesn't do the building owner or occupant any favors if we design our system for light hazard, which requires a density of 0.10 gallons per minute over an area of 1,500 square feet and requires a hose allowance of 100 GPM, when the occupancy hazard class is really ordinary hazard group 2, which requires a density of 0.20 over 1,500 square feet with a hose allowance of 250 GPM. That would be a pretty big problem and cost a lot of money hydraulically reinforcing the system later on. NFPA 13 requires a document called the Owner Certificate be provided to the system designer to aid us in identifying the correct occupancy hazard class. In my area of practice, only one AHJ actually requires this document to be submitted with the system plans and calculations, but I've gotten to where I require it on everything to make sure we get it right. Once we have that, it goes into the project folder along with the water supply info. Sprinklers. Too many times it seems that sprinkler selection is an afterthought. Really, this is where the rubber meets the road. These little appliances are what puts the wet stuff on the red stuff, as we used to say in the fire department. In our industry, a lot of people refer to these as sprinkler heads or just heads. Earlier in my fire protection engineering journey, I worked in insurance loss control. My mentor and the VP of engineering was a very respected member of NFPA 13, and he would reject a loss control engineering report if I used the term sprinkler heads or heads, because those terms do not appear in NFPA 13. So, for the purposes of me teaching these segments, I'll use the term sprinkler, old habits and all. Not all sprinklers are created equal, but every single one out there has a part to play. What we care about are the hydraulic properties of a sprinkler and the listing of the sprinkler. Whether we're calculating a sprinkler system we have designed or calculating a system after the fact to determine hydraulic adequacy, these are very important data points that we must know. For a sprinkler's hydraulic characteristics, oftentimes the most important bit of information is the K factor. Like we briefly discussed in the last segment, the K factor is a coefficient number that corresponds to the flow characteristics through the sprinkler's orifice. The larger the K factor, the larger the orifice, and vice versa. We need to make sure we have this correct. Further, for non-standard spray sprinklers, extended coverage sprinklers, special application sprinklers, or sprinklers protecting high-piled storage in an ESFR system or control mode special application design, we need to know the pressure that the sprinkler needs to operate at. This can seem like a pretty insignificant data point, but it can really make a huge difference. For example, if I designed a system protecting a light hazard area using K5.6 standard coverage sprinklers with 14 by 14 sprinkler spacing, I'm probably going to be fine with the NFPA 13 minimum sprinkler pressure of 7 psi. But if I'm protecting that same area using K11.2 extended coverage sprinklers maxed out at 20 by 20 feet, the data sheet says that I need a minimum of 12.8 psi at each sprinkler. That's a pretty big difference, and I need to get that right. If you're the one designing the system from the ground up, you probably have this covered. However, if you're trying to reverse engineer the system and calculate it to determine its hydraulic adequacy, this might take a little work. It's best to do what it takes to find the sprinkler SIN, and every sprinkler has one. The SIN is the sprinkler identification number. Once you have it, you can look it up and find out everything you'd ever want to know. As for a sprinkler's listing, well, it has no value in calculating your system. If you're the one designing the system, you want to ensure the sprinkler is listed to do what you want it to do. Sprinkler coverage. Sprinkler coverage, or the square footage of floor space each sprinkler is designed to protect, is a critical component of our hydraulic calculations. Years ago, there was an old MS-DOS hydraulic calculation program called HyperCalc. It was pretty keystroke intense and a far cry from some of the hydraulic design software available today, but it worked. All it did really is show you what the most demanding sprinkler was, and then the user was responsible for the actual calculation. The hydraulic equation to find density is the square root of the pressure available at the most demanding sprinkler multiplied by the K factor of the sprinklers and then divided by the square footage each sprinkler covers. As an example, let's look at that hypothetical light hazard area. Like we said, we'll need a density of 0.10 over 1,500 square feet. we're going to say that we designed this with K5.6 standard coverage pendant sprinklers spaced at our maximum allowable 15 by 15 spacing for 220 square foot coverage. For easy math, we're going to say that our most demanding sprinkler is right at the NFPA minimum allowable pressure of 7 psi. The density equation looks like this. Square root of 7 psi times 5.6 divided by 225 square feet equals 0.065. Well, that's not good. We need 0.10 and we only have 65% of our required density. Back to the drawing board. So we redesigned it, and this time we reduced our spacing to 12 by 12 for 144 square feet of coverage per sprinkler. Magically, our most demanding sprinkler is again right at the NFPA minimum of 7 psi. Let's look at the math again. Square root of 7 times 5.6 divided by 144 square feet equals 0.102. Hey, we got it! Yay us! I never doubted us, not even once. Now, that's a pretty basic equation. In the real world, there will be some other things we need to address, but the reason we went through this exercise is to illustrate that sprinkler coverage is a critical component of the sprinkler hydraulic calc. The only thing we changed is our coverage and spacing, and we went from hydraulically inadequate to adequate. Sprinkler pipe. Another factor in getting ready to calculate a system is identifying the sprinkler pipe. If you're designing the system from scratch, you probably have this covered. But if you're reverse engineering the system, you need to know this. If the system is using metallic pipe like black steel, you need to know the schedule of pipe. Like we touched upon in the first segment, Schedule 7, Schedule 10, and Schedule 40 metal pipe are very common. The higher the number, the thicker the pipe walls are, and the smaller the inside diameter of our pipe becomes. Pipe with smaller inside diameter will generate a higher friction loss per foot than pipe with a larger inside diameter. Using 1-inch Schedule 40 threaded pipe for pendant drops is very common, even when the rest of the system is Schedule 7 or Schedule 10. Most 13R and 13D systems, and even light hazard systems, will use CPVC plastic pipe. Sometimes systems will use a combination of all of these. If you're sketching a system in the field to calculate it later, it's important to identify all of this ahead of time. We'd probably want to avoid just looking up at one point in the system and seeing a 4-inch cross main and assume all of it is 4-inch. We'd hate to miss a 6-inch cross main closer to the riser or a smaller main diameter further in the system. Type of system. This part is pretty easy. We need to know if we're calculating a wet system or a dry system. This is important because the C factor is different for a wet system than for a dry system. The C factor is a coefficient we use to account for the roughness on the inside of the pipe. We presume that piping in a dry system has a lot more rust and scale and other gunk sticking to the sides of the inside of the pipe, and we need to account for that. The C factor is how we do that. Other series in the MeyerFire University program go into a lot of detail with this, so I would encourage you to check those out. Remote area. In the first segment, we discussed the hydraulic remote area and how this doesn't necessarily correlate to the most physically remote area. We also discussed the shape of the remote area. Prior to calculating our system, there's something we need to identify. It's unlikely that any of us are running these calcs by hand, and today's hydraulic software makes it really easy to do this. Now, I do want to point out that throughout this series, I'll use the default remote area size of 1,500 square feet. However, that isn't always the case. For calculating a dry system or a pre-action system or a system with steeply sloped roof or ceiling, we will need to increase the remote area size by 30% to 1,950 square feet to account for the delay there will be in getting the water to the opening sprinklers. Additionally, in light hazard and ordinary hazard Group 1 and Group 2 systems, we can decrease the size of the remote area by quite a bit if the ceiling or deck height is less than 20 feet and we're using listed quick response sprinklers. As an example, if we have a light hazard system with 10-foot ceilings, our remote area can be decreased to only 900 square feet. Once we know where our remote area is located, we have identified and quantified everything we need to calculate our system. These are pretty much an overview of the information we need to identify and organize prior to making our hydraulic calculation. We need the foundation of our design, which is the water supply. We need to know what our occupancy hazard class is in order to know the density our system needs to provide. We need to know what sprinklers we're going to use and identify things like K factor and know if this specific sprinkler needs to be flowing at a specified pressure or flow. We also need to know how much square footage each sprinkler is covering. We need to account for the sprinkler pipe used to supply our sprinklers because different schedules of pipe have differing inside diameters. We also need to know if this is a wet system or a dry system so that we use the correct corresponding C-factor. Finally, we need to find out where our remote area is. And there you have it. That's the information we need to compile and organize to calculate our system. I'm Jesse Cecil. This is MeyerFire University.
This has been a preview of MeyerFire University. Join the next generation of fire protection experts at www.meyerfireuniversity.com.